Good morning. It's morning for me. Welcome to the paper reading stream today. So checking my levels, just gonna really quickly make sure that everything catches up. Hi, how's everybody doing? Okay, that looks good. Looks like it's working. Audio levels look okay. Let me know if you can't hear me. I guess you wouldn't hear me saying that if you can't hear me. This is a paper that we started in July. And I promptly forgot to finish it. I feel like I was off the next week or something. Anyway, we never finished it, so we're gonna finish it today. Well, we're gonna make more progress today. I don't know that we're actually gonna finish it. So this paper is about, once we read the abstract, I think it makes sense. It is from ICLR 2020, which is a big conference on machine learning. I think LR stands for learning representation specifically. And it's out of Google Research and Berkeley. And ICLR was several months ago. Hi, Robbie, how's it going? So, transformer models are a class of models that have a lot of attention over a specific time. No, it's not really time span. Over a sequence of items, you have attention between all the items and a bunch of learned weights, and they have a lot of learned parameters associated with them. So having a way to, oh, long that's my earrings. Thank you. They're little astronauts. So having a way to reduce the total number of parameters that you have in a model, particularly a transformer model, never a dull moment. I don't know if you can hear my dog barking. So having a way to reduce the number of parameters you have in a model, particularly a transformer model, has the potential to really improve the size and the speed at which the size of the models and the speed at which they want, and also just makes them less expensive to train. So as an example of a very expensive model, GPT-3 is a transformer model that has, I don't know, some estimates have put it at like $20 million worth of compute time. So just training on machines, which is a lot. Also, it's big, and there's some. That particular model has some other problems with it. So there's a paper out of NeurIPS, which is this week, which is another big machine learning conference, looking at sort of anti-Muslim bias in GPT-3 and sort of quantifying that, and it's really bad. Anyway, so this paper is trying to address this problem of, okay, these models are really big, they're very expensive, they do seem to work well, but can we get, you know, similar performance with a smaller model? So to read the abstract, he's going to say basically that. He's calling you? No, I think he heard something. He wanted to tell to leave. Large transformer models routinely achieve state-of-the-art results on a number of tasks, but training these models can be prohibitively costly, especially on long sequences, which I think they're going to talk about the degree to which that is costly. For one, we replace dot product attention by one that uses locality-sensitive hashing, changing its complexity from OL squared to OL log n, where L is the length of the sequence. So if you had a sequence of 4, your complexity would, instead of 16, be 2 to the log of 2, and I can't do that in my head. Maybe I could have at one point. Less is what I'm saying here. So faster, fewer operations. Furthermore, we use reversible residual layers instead of the standard residuals, which allows storing activations only once in the training process instead of n times, where n is the number of layers. The resulting model, the reformer, performs on par with transformer models while being much more memory efficient and much faster on long sequences. So they're saying that we have some architecture changes that we're proposing And I vaguely remember this locality sensitive hashing, and I don't remember the reversible residual layer. So I think we probably got through locality sensitive hashing and did not get through the residual layers. So let's just quickly skim through the bit of this. Could I have gone back and watched the video from July? Yes. Did I intend to? Yes. Did I get to it? No, I didn't. That's okay. So this is the standard attention, and basically every item in the sequence attends to every other item in the sequence. That attention is mediated by sort of 3 tables that are all the length of the sequence, and all the values in the tables are learned. That was something that was very confusing to me when I first started with transformers, is that usually if you have, you know, something that you're querying, that's decided a priori, and then you're sort of looking it up at runtime. But the queries, keys, and values, all of these, every value in those is learned through, you know, the way that you're doing your learning. And then multi-headed attention, you don't have just a single attention, you have multiple ones. The number of heads is a hyperparameter that you would pick. And then they so they're talking about the different ways that it's stored and the size of it, and that it is really big and doesn't work super well for long sequences, which is the case. And their hashing attention, I vaguely remember this. So for this, you project your points onto a circle, and then you divide your, you know, Cartesian plane into 4. And then you look and you see which of the quadrants each of your points is in, and that tells you how close they are to each other on, you know, whatever dimension you've projected them on. And I do remember going over this. This is still in the old oatmeal pot. And the method is known as LSH Scheme, so locality sensitive hashing, and it's easy to implement. Okay, and that's about as far as I remember. I don't... Oh, no, I do remember this. Yeah. So you look at the bucketing. You look at where in the circle quadrants each key was stuck, and then you have, so here we see the queries have been sorted based on their hash, and the keys have been sorted based on their hash. So instead of being randomly distributed, they are next to each other. And for this, it's been made symmetrical by just having reflecting Q down to K. And here, I don't know how they're chunking this. I don't remember talking about this. I vaguely remember this reflection thing. It's been several months of not the best brain time for me, I would say. Okay, so the attention, instead of every item attending to every other item, it only attends to items that are local to it, and locality is determined by the bucketing, the chunking, and you attend to every item in your current chunk, and okay, attend within the same bucket to its own chunk and previous chunk. Got it. So it's like, okay, so why is only this blue one attending backwards? So this blue one is paying attention to things from the same bucket from the previous chunk, and same here with the yellow. The yellow is also attending to items from the previous chunk, but the white is not, because the white bucket doesn't have any matching items in the previous chunk. So the white items in the white bucket are only attending to the current chunk because there are no objects from that same bucket in the previous chunk. Yeah. And red is only attending to other red sequences because it's not in the same bucket as yellow. Yeah. Okay. This makes sense. This is following. And if we had, let's say, you know, 12 blue ones, these blue ones would attend to themselves. These blue ones would attend to all of these and all of these, and then these blue ones would attend to all of these and all of these, but not all of these, because it only looks back one chunk. So basically you just have a lot fewer, you know, values you have to store, a lot fewer attention items, and you can get rid of stuff. So instead of every single one of these squares being computed, and both the Q and the K and the V being computed, instead you only compute these items here, right? So only the filled in squares, which dramatically reduces the number of computations to the order of OL log L. So many, many fewer computations. Yes. Okay, so that makes sense. And this this LSH attention is based on locality sensitive hashing, which is something that these authors are applying here, but was not developed by them. That was from an earlier work. I vaguely remember this. Okay. So let's jump back in just here. So in the description of figure 2, A through B. There's a schematic comparison of full attention with a hashed variant. So this is full attention, all these squares are computed. This is the hashed variant, only the filled squares are computed, if I'm right about this. Part A depicts the attention matrix for full attention, depicts the attention matrix for full attention is typically sparse, but the computation does not take advantage of this sparsity. So the ones without dots, the value there is just 0, but it's still being computed and it's still being learned. So you don't take advantage of the fact that there's a bunch of zeros here. You still treat each of the zeros as if it might be a number of interest to you. Hi, land coding, and welcome to the stream. Okay, that makes sense to me. This is, I don't know, there's something about this. Maybe it's because the last coding interview I studied for was at Google that just is like bringing me back to my last coding interview. Which was awful. There was a dramatic mismatch between the person, well, some of the people who interviewed me and my particular role and ladder. It was not great. Anyway, doop-a-doop-a-doop. So typically sparse, lots of zeros. Let's treat them like they're not there and avoid computing them all at once. In B, the queries and keys have been sorted according to their hash bucket. Since similar items fall in the same bucket with high probability, the full attention pattern can be approximated by only allowing attention within each bucket. The bucket here being the quadrant of the circle, boop, 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 based on this projection, and random rotation, and here that is represented by colors. So each of these colors is a different bucket. Hash buckets in this formulation tend to be uneven in size because the points are not going to be distributed evenly. I guess there's a situation where they might be distributed evenly, but that certainly isn't a good approximation of linguistic patterns for sure, which is where transformers tend to be used most often. I've started learning Rasa and I don't know how to emulate APK. Can you explain? No, I also don't know how to do that. I would post on the forum, which is... I'll pull it up for you real quick. Did I? Nope, I didn't. I made some little animations, but I didn't put one on this particular scene. But that forum will be forum.rasa.com. So I would post that there and you'll probably get better results. I know you will, because I just don't know. Okay, so... blah, 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 blah. Moreover, the number of queries and the number of keys within a bucket may be unequal. In fact, it is possible for a bucket to contain many queries, but no keys. Oh, I got you. Okay, so this is why they're doing this reflection here. So here we have, for example, this bucket has 1 key and 3 queries. This bucket has 2 queries and 2 keys. This bucket has 3 keys and 1 query. So they're sort of very rectangular, or you might end up with, you know, none keys in a specific bucket, but you do have queries in it. So we get rid of this by reflecting across the median. Yes, to alleviate this issue, we first ensure that HKJ equals HQJ. I believe this is the dimensions? I think that's the size? Where did H come from? When did we talk about H last? Hash. Oh, okay, so the size of the hash KJ is the same as the size of the hash QJ by setting KJ equals QJ divided by the absolute value of QJ. Next, we sort the queries by bucket number, and within that's not absolute value. That's something different. Next, we sort the queries by bucket number, and within each bucket by sequence position. This defines the permutation where I funky arrow S after sorting. I see. I don't know what that means. In the second attention matrix, pairs from the same bucket will cluster near the diagonal, as depicted in figure 2c. We can follow a batching approach where chunks of m consecutive queries after sorting attend to each other and 1 chunk back. Following our earlier notation, that corresponds to this. So that's this bit where each chunk is attending to things from its bucket in its current chunk and the previous chunk. If max I of P is less than M, then P, what's P here then? What does this mean? Okay, so if, the max of the absolute value of P here being the number of buckets, the number of chunks, less than the length of the sequence, then P is in the set of tilde P's. Yeah, I'm not picking up what they're putting down right there. In practice, we set M to 2L divided by the number of buckets. So M must be 2 times the sequence length divided by the number of buckets. Okay, gotcha. So M here is the size of these chunks. How many items are in each chunk? So here it would be 4. So if the max less than the size, the average bucket size is the length divided by the number of buckets. That makes sense. The length of the sequence divided by the number of buckets. And then we assume the probability of a bucket growing to twice that size is sufficiently low. The overall process of LSH attention is summarized in figure 2. Okay, so this is what they're doing, and this is the notation for it, and I'm not entirely following the notation. Here they're talking about some of the hyperparameters that you might want to change here. Okay, so what is... Oh, here we go. Okay, so PI is the set of target items in a query position I can attend to. Okay, so P is the number of things a single item can attend to. M is the size, the number of things in each of the buckets. And sorry, not each of the buckets, each of the chunks. So buckets are based on the projection of the quadrant. Chunks are something separate. The size of the chunk is a hyperparameter that you choose. Here they're saying that as long as the number of things that something can attend to is less than the number of chunks, then a single item's attention will fall into this set that they're defining here, I think is what that's saying. In practice, we set M to be twice the length divided by the number of buckets. So we're not going to reach the situation where you have 3 chunks all the same. You're going to reach a situation where maximum you have, on average, the maximum number of chunks in a row that will have the same bucket in them is going to be 2. That's what this bit is. Okay, and then we assume the probability of a bucket going to twice that size is sufficiently low. The overall process is summarized in figure 2. Okay, so that makes sense to me. That's how they're doing attention, and that's how they're avoiding the thing where they just say every item attends to every other item, and we're just going to compute all of those things, and there will be so many, and we're going to have to store them all in memory, and we're going to have to update them all every pass. Even if we're just changing them from 0 to 0, we still need to run that pass and do those computations. So we're not doing that. We're only doing some of them, and we're picking the most important ones using this process to take advantage of the sparsity. With hashing, there is always a small probability that similar items nevertheless fall into different buckets. So here, where these 2 items are very close together on this projection, you can't imagine a situation where they one item falls here, one item falls there. Even though they're very close to each other, they end up in different buckets, is what they're saying. This probability can be reduced by doing multiple rounds of hashing with n rounds distinct hash functions. The multi-round case essentially involves performing LSLS attention n rounds time in parallel. The details of the procedure are described in Appendix A. Okay, so you see how we have like 2 here, right? These are both done 2 times, and then making sure that, well, I guess the more details are in the appendix, but it looks like here we're going to run it a number of times that we are doing based on a hyperparameter that we're setting, and by repeating it multiple times, even if we get a situation where we have like 2 things that are close together and they end up in different buckets, if we do it enough times, we should be able to see, okay, usually these are always in the same bucket, so we can assume that these are close. These are almost never in the same buckets, so we can assume that these are farther apart. That's what they're saying there. What's the paper? Oh, yeah, I don't think I updated the link, so it's the one that's above me. Reformer, the Efficient Transformer from ICLR 2020. Okay. So causal masking for shared QK attention. So sharing the queries and the keys. In a transformer decoder, masking, denoted by MJP in equation 3, is used to prevent positions from attending to the future. So if you are, generating language 1 word at a time, you can't see what word you generated 3 words from now and use that to decide what you're going to do currently, because that's not how time works, which is why you would want to prevent this sort of behavior. To implement masking in LSH attention, we associate every query key vector with a position index, reorder the position indices using the same permutations used to sort query key vectors, and then use a comparison operation to compute the mask. So what they're saying is the reason that all of the arrows are pointing backwards is that when we're shuffling things, we have a memory of what happened first, second, and so on. So here, Q1 happened before Q2, happened before Q4, Q3 happened before Q6, and so on. And then, yeah, that's what I'm getting from that. And that means that that, x plus 2 did not cause x plus 1 because it happened after, if that makes sense. Okay, so that's what they're saying. And then they have some tables. While attention to the future is not allowed, typical implementations of the transformer do allow a position to attend to itself. Such behavior is undesirable in a shared QK formulation because the dot product of the query vector with itself will almost always be greater than the dot product of a query vector with a vector at another position. We therefore modify the masking to forbid a token from attending to itself, except in situations where a token has no other valid attention targets, e.g. the first token in a sequence. That seems reasonable. Analysis on a synthetic task. To verify the performance of LSH attention and study its behavior, we start with the following synthetic task. Duplicate a sequence of symbols. In this task, each training and testing example has the form OW, where W is in the set of 1 through n, is a sequence of symbols ranging from 1 through n. We use n equals 127 in our experiments. An example would be the word W with a length of 3 given below. So we have 0, our word is 19, 113, 72. 0, our next word is 19, 113, 72. And okay, so the word is being repeated and you want your transformer to also repeat the word. To study LSH attention, we train a language model on examples of the above form where each W is of length 511, so it's a big one. So the whole input is of length 1024 to make it, easier to fit in memory. As this is a language modeling task, we always predict the next symbol given all the previous ones, but we mask the loss and accuracy to only consider positions in the second half of the input, i.e. those that can actually be predicted. So we have basically a random word. You wouldn't be able to, if I was like, hey, the first 2 letters are 19, 113, what is the next letter going to be? You probably wouldn't guess 72 because it's not really predictable because this is generated randomly. But if I was like, hey, the word you're repeating is 113, 19, 113, 72, what's the word? You can guess it with a high accuracy, is what they're saying there. The above task can be solved perfectly to accuracy 100% and loss 0 by a 1-layer transformer model. Note, though, that it requires non-local attention lookups, so it cannot be solved by any model relying on sparse attention with a limited span. So if you had something like, an RNN that had sparse attention, it wouldn't be able to work as well, is what they're saying. To make it easy and fast to train, but similar to models used in NLP, we used a 1-layer transformer with D model equals DFF equals 256, so 256 dimensions with 4 heads. We train it for 150K steps in 4 different settings. With full attention, so the most expensive one, locality sensitive hashing attention with the number of rounds being 1, the number of rounds being 2, and the number of rounds being 4. So LSH, we only take 1 sample, would be 1. We spin our wheel and see where things end up 2 times, or we spin our wheel and see where things end up 4 times. And the higher n is, the more likely it is that you're going to categorize things that are similar together. Is why you would do that multiple times. From the results summarized in Table 2, we see that a model trained with full attention can be immediately used with LSH attention, but at some loss of accuracy. When trained from scratch with LSH attention, the model trained with 4 hashes achieved almost perfect accuracy as well. Interestingly, the accuracy becomes perfect when evaluated with 8 hashes, so if you kept spinning the wheel 8 times. It goes down when evaluated with 2 or 1 hashes, because there's that possibility that things are going to end up in different bins. Models trained with less hashes show worse results, but even the model trained with just 1 hash performs almost perfectly when evaluated with 8 hashes. Okay, so this is a difference between training time and evaluation time. All right, and that's in here. Oh, and here they're just talking about the time complexity. And what you should get from here is that the LSH attention is faster. Oh, so time and memory complexity. So how much storage does it take and how long does it take to run? All right, so here is their model. So here is the training. Was it trained with full attention, LSH1, 4, 2, or 1? Full attention, it does perfectly. And for evaluation, oh, that's interesting. Sorry, the thing that I'm noticing is that if you train with this locality sensitive hashing, right, and then evaluate with the locality sensitive hashing, you get better results, right, than the model trained with full attention. So it looks like if you're evaluating, if your model is trained with locality sensitive hashing and you're evaluating with locality sensitive hashing, you'll get better performance than you would evaluating with locality sensitive hashing and a full attention, a model that was trained with full attention, which is not necessarily expected, right? Or at least not by me, because a model trained with full attention has the most weights, right? It has the most ways to store the information. It was the most expensive to train, and it's also the most expensive to run because there's the most computations, and it's the hardest to fit in memory because it's the biggest. And it doesn't perform better than, in fact, it performs worse if you are giving it these LSH inputs during evaluation time. Whereas the models that were trained with LSH do better with the LSH inputs. And the reason that that's important is because these are smaller. So it's going to be easier to run and cheaper. Interesting. All right, analysis on a synthetic task. We already read this. Yeah. Okay, reversible transformer. On section 3, and then related work, and then experiments. Okay, we might actually finish this today. And I know it looks longer than it is. It's just because there's a lot of appendices in this one. Okay, so I think that's very heartening, because if you're using this method, both at train and test time, you could see really significant memory and time, savings with equivalent results, as long as you do enough spins of your little hashing wheel when it's evaluation time, which I think is cool and interesting and makes me want to use this, right? I mean, especially for something like an embedded system where you're not going to necessarily be able to, it's going to cost you money to send, a bunch of API queries with like big chunky data bits in them, or to run. I think that this could be a real benefit in that sort of situation. All right, reversible transformer. As the above section shows, the complexity of attention can be reduced from square in length to linear, provided an approximation is acceptable. But it is clear from table 1 that each field starts with B times NH times L term. The B, NH, L, DK, or alternatively BLD model cost cannot be avoided. So this is the length of the sequence, this is the dimensions of the model, and B is something. Is that the number of heads? That's a wild way to represent the number of heads. What's B? Let's go up and see if we can find it real quick. I feel like we've read it and I've just immediately forgotten it. The dimensions of the model. All right, that's the memory. The number of buckets, maybe? That would make sense. Or is it batch size? Yes, okay, that's batch size. That makes a lot of sense. So this is something that you would do when you were training the model. Gotcha. Okay, so using this approach, you're going to get, it's going to be easier, but you need to start, this is like the minimum size that it could be, is the batch size times the the length of the input times the dimensions of the model. Indeed, the activations before each layer are already of the size BLD model. So the memory use of the whole model with NL layers is at least BLD model NL. And that's the dot product. So that is, sorry, I'm adjusting. That's big. That's a lot of dimensions, right? And the dot product means you compute all of the intersections there. Intersection isn't the name. I forget the name. But you do all of them. Even worse, inside the feed-forward layers of the transformers, this goes up to BLDFF-NL. In a big transformer, it is usual to set DFF equals 4K and L16. So with L64, this again would use an impractical 16 gigabytes of memory. Imagine trying to fit that on your phone. Jiminy Cricket. In this section, we show how to reduce the cost by first dealing with the NL part of the term using reversible layers, and then showing how chunking can allow us to handle the DFF problem. The effects of each of these approaches on memory and time complexity are summarized in Table 3. So they're saying, hey, we can do a lot fewer computations, we can take advantage of the sparsity, we still have this really big input, how are we going to make it a little bit more manageable sized? Revnets. Reversible residual networks were introduced by Gomez et al. 2017, where it was shown that they can replace ResNets for image classification. This is literature I have never touched. I hope they talk about it in detail because I'm not familiar with this at all. The main idea is to allow the activations at any given layer to be recovered from the activations of the following layer using only the model parameters. Rather than having to checkpoint intermediate values for use in the backward past, layers can be reversed one by one as backpropagation proceeds from the output of the network to its input. Whereas a normal residual layer performs the function xy that operates on a single input and produces a single output that has the form y equals x plus f of x, a reversible layer works on pairs of inputs and outputs. Okay, so what they're saying is, usual way of doing it is during your backwards past, you've got all your values, you update them for the next layer, you compute and store them, next layer, compute and store, next layer, compute and store, and you're doing that one by one. And they're saying that the instead of storing all those intermediate values, you just peek at what happened before, use that to figure out what you're doing, and then I guess forget the things that you did before because you're going down to the next level, I think is what they're saying here. All right, so you've got pairs of inputs, x1, x2, y1, y2, where y1 equals x1 plus f of x2, and y2 equals x plus g of y1. So you figure out what y2 is given x1 and x2, and then you figure out what y2 is given x2 and y1, and then having some functions. And then later, you know what these are, so you can reverse that operation and undo it. We apply the RevNet idea to the transformer by combining the attention and feed-forward layers inside the RevNet block. In the notation above, F becomes an attention layer, while G becomes a feed-forward layer. Note that the layer normalization is moved inside the residual blocks. The reversible transformer does not need to store activations in each layer, so it gets rid of the NL term. In section 5, we show that it performs the same as the normal transformer when using the same number of parameters. We achieve this by having both x1 and x2 have size D model. So this is not changing the number of computations you need to do. It's just saying, hey, you don't need to store these values because you can just reverse the process that you did earlier and get them back. So this is changing the memory complexity, not the time complexity. What changed the time complexity was that we weren't attending to as many things because we took advantage of the sparsity of the attention using the locality sensitive hashing. I'm picking up what they're putting down. I would say that this paper is like very slightly outside of my core area of training. It's really well written. I'm following it really well. So kudos to the authors. Good paper. Chunking. Well, reversibility covers the NL term. So basically, they're like, hey, right now, this is how big our memory needs to be. Wowie, that's a lot of, you know, that's a big tensor. So we're going to try and make each of these numbers as small as possible so that we can have, you know, the smallest memory footprint possible so that our trained model isn't 16 gigabytes. To put that in contrast, like, I don't even know off the top of my head like how big like a Markov chain model would be, because it is inconsequential. It's so small, it doesn't matter. And it's like I could run that on a phone, no problem, nice and compact, as compared to the transformer models, which are, I would say, not nice and compact if I had to describe them. Not the words I would use. Big, slow, and expensive, I think, is what I would use to describe transformers, the traditional sort of like language models. I don't know that they're traditional, commonly typed. Okay, so how do we get the different things down? So we've gotten down the, we've gotten rid of having to store all of the intermediate levels because we can just recompute them whenever we need them. We apply chunking. While the reversibility covers the NL term, the thicker layers can still use a lot of memory. The feed-forward layer in particular can use intermediate vectors of dimensionality DFF equals 4K, so the dimension of the model, I think, or higher. However, computations in feed-forward layers are completely independent across positions in a sequence, so the computation can be split into C chunks. So as we're stepping across the sequence, we don't need to keep all of the things in memory. Okay, so I'm getting that they're going to say that we can do our computation and then forget that, and then do the next computation, and then forget that, and then do the next computation. I'm guessing is what they're going to say here. This layer is typically batched by performing operations for all positions in parallel, but operating on one chunk at a time can reduce memory. Yeah. We're on the same wavelength. The reverse computation in 8 and the backward pass are also chunked. In addition to the feed-forward layers for models with large vocabulary, more than D model word types, we also chunk the log probabilities at output and calculate the loss for sections of the sequence at a time. Excuse me. Okay, so they're saying, so we're chunking the feed-forward parts of the model, and we're also doing the backward pass from the second, the one above, where you just recompute it every time and you don't store it in memory. And we're also chunking the log probabilities at the output. So if there's a lot of different words, you're looking at each of the outputs separately and then calculating the loss for sections of the sequence at a time. So instead of doing the loss for the whole sequence, do loss for section, do loss for section, do loss for section at each point, forgetting, you know, all of the things that you held in memory prior, and then, you know, taking those and combining them into the grand loss, I would say. Chunking, large batches, and parameter reuse. With chunking and reversible layers, the memory we use for activations in the whole network is independent of the number of layers. That makes sense because at each layer, because you're doing chunking, you perform your computations and then you don't have to store, you only have to store the output. You don't have to store all the intermediate values in memory, and you can just forget them and then recompute them the next time. And I mean, you have to recompute them anyway, right? Because you're updating them every time, but you don't have to, you know, store all of them in memory. This problem is remedied though. Oh, I skipped a sentence. The same is not true for parameters, though, as their number grows with the number of layers. This problem is remedied, though, because we can swap layer parameters to and from CPU memory when this layer is not computing. Okay, so we've been talking about the activations. You still have the parameters. And what they're saying is, like, if you had, you know, everything's in CPU memory, okay, I need to pick this layer, take it out, compute it, put it back into CPU memory, don't keep it in, I guess, GPU. and then continuing to do that with every layer so that we have a really efficient use of memory. In a standard transformer, this would be inefficient because memory transfer to CPU is slow. The batch size multiplied by length in Reformer is much larger though, and therefore the amount of compute done with the parameter amortizes the cost of the transfer. They're saying, okay, yes, transfer is slow, but because we're doing so many more calculations so much faster, we end up with an overall time benefit, I think is what that's saying. Okay. And then here are the summaries of the memory and time complexity. What they're saying is that as you add more and more of the stuff that they're proposing here, it gets better and better. And yeah, both memory and complexity. Memory and time complexity for the transformer variance. We write D model and DFF for model depth and assume that DFF is greater than or equal to the dimension of the model. B stands for batch size, L for length, N for the number of layers. We assume that NC equals L divided by 32, so 4L divided by NC equals 128, and we write C equals 128 squared. Cool. Okay, so the things that they're doing to make things more efficient. A, we're not computing, the full attention matrix. We're only looking at things that are close to the thing that we are currently using, right? Also, and that works well. Also, we are, rather than specifically for attention, I should say that we're talking about attention rather than the parameter values. At each layer, we are computing them via a reversible process, and then we're not storing the values, for all of the layers. We're just storing the ones that we need, and then computing the next one, and then getting rid of the ones that we don't need to store in memory to reduce memory size. And then for chunking, for the feed forward layer, just in particular, instead of computing it all at once in parallel, which is sort of what's done by convention, they're chunking it up, and then as they do each chunk, saving the output, and then getting rid of the intermediate values, and also they're storing the chunks that they're not using in the CPU, and it does take time to transfer between CPU and I said GPU, probably TPU actually, if I was guessing based on the lab. They're pulling them in, doing their transformations, and then putting them back out and getting the next one. And even though that's slow, because of the other efficiencies, they don't see a huge time increase, and they see a really good benefit in memory complexity. Whew. There's a lot going on in this paper. And then related work and experiments. So let me see we got about 10 minutes. Okay, so I'm just gonna skip the related work, I think. So these are just talking about the, history of transformers, Vaswani proposed them. This is the BERT paper. Pretty sure this is the GPT-3 paper, right? Is that the GPT-3 paper? Yeah, that's a GPT-3 paper. It's this model, people use them. There's been a lot of people being like, hey, they're really big. There's some methods such as precision reduction and gradient checkpointing, and also more efficient methods of self-attention. So other work that's been done on making transformer models more efficient. And then a lot of work on leveraging sparsity, because you don't, even though in the traditional model, the sort of the vanilla transformer, you're computing all the attention weights, most of them are going to be 0. So out of OpenAI, a sparse model, which I am not familiar with, and then using product key attention to increase the key space has also been used to reduce memory requirements with no loss in performance. All right. So just different ways of making transformers smaller. Robbie says all deep learning is run in a distributed way. Not necessarily. locality sensitive hashing. So this method that they use that was proposed by someone else. This is, to their knowledge, the first time it's been applied to transformer attention layers, but there's a lot of previous work using external memory with neural networks. And then later scaling it and work there. From 2014, which is a pretty early citation. I think especially transformer, Bert, it needs more computation. Yeah, I mean, yes, a lot of models are trained in a distributed way, but I wouldn't necessarily say that all are, and you know, particularly for people who are working on specific projects, they may have requirements that make it difficult or impossible to train a model or serve a model in a distributed way that works with them. So just as an example, if you have sensitive data that you would not be able to you know, use a cloud provider for, and also you can't afford the equipment that you would need for distributed processing, there's lots of people that are training these models in a not distributed way for whom things like BERT are just straight up out of reach, but you know, just like deeply impractical. So I think that this paper is helping to address some of those problems, which are, you know, pretty big problems in the field. Okay, and then more discussion. And just sort of more work that they're building on that I am unfamiliar with. Yeah, so it looks like it's part of a larger tradition of doing things in a more efficient, memory efficient way. Then the experiments. I'm just gonna skim this, I think. So they ran ImageNet 64 and IngWiki 64K tasks. I'm not super familiar with this task. I would call this more of a data set. TPUs only for Kaggle competition. I mean, TPUs are a piece of hardware specifically designed for tensors. And I mean, you can use them for, I don't want to say like necessarily any tensors, because I don't know that, you know, all the libraries that you might want to use are going to be supported. And also, I don't know that you can like buy a physical TPU to own either. It might be one of those things you can only rent time on. They're out of Google if you're unfamiliar. Yeah, I was more familiar with them in the past and have not kept up with stuff. All right, and then a bunch of their parameters. Okay, so here they're showing that doing that thing where they reflect the key in query to avoid situations where you have something that has, you know, a bucket that shows up only in the queries or a bucket that shows up only in the keys. On performance, the curves show bits per dim on held out data. Okay, so this must be a this must be evaluated like a language modeling task, right? Like how well are you able to capture the distribution of the input thing? I'm guessing. Like I said, I'm not super familiar with either of these tasks, but I think what they're showing here is that hey, if you share the steps. Oh, actually, so if you share them, it's better. You get sort of convergence faster, making your model reversible, so reducing the amount of, you know, intermediate steps you're holding in memory for attention. Doesn't change model performance pretty much at all. And then, so this is for IngWiki, the English language wiki data. Again, I don't really know what the task is. It looks like they might be measuring entropy, I guess. And then same deal for, oh, actually it doesn't work quite as well for the image data as it does for the language data, but there's not really a major difference. And they're just showing that, hey, these changes that we've made to make stuff more efficient isn't really, you know, harming model performance. And then some blue scores, and then some detokenized blue scores, and they're showing, hey, our model is like, this is their model. Our model is, you know, really close to these other models, and actually a couple of them, this one, the big with no weight sharing is outperforming the 2017 Viswani models. And I'm not familiar with Sacra Blue. Yeah, again, I'm not entirely sure what the tasks are here, but basically what they're showing is like, hey, here's how previous folks did on this their task with their models. Our model is doing pretty much the same. And then here, I'm guessing lower is better here because as the number of steps increase, this is going down. Oh, okay, and here they're saying, so full attention, which is this dark line here that's at the bottom, which looks like it's doing the best, but at an enormous memory cost. And then the number of sort of like hash samplings that you're doing. And this gray here is, you know, tracking the full attention really closely. 8, you know, a little bit worse, but again, pretty close. 4, a little bit worse, and then 2, a little bit worse. So the more hashes you can do, the closer your performance is going to be to the full attention model. And then layers, more layers do better. And then the speed of attention evaluation as a function of the input length. So this one I think is a particularly interesting. Matthias says Rasa's rocket chat integration. Not super familiar. I would ask about that on the forum if you have a specific question. But this I think is a really interesting point, because as you can see, as the number as the sequence length goes up and the batch length goes down, there's sort of this, you know, increase in speed. So the full attention model is not able to capture, you know, the full attention model gets really slow when the sequences get really long, whereas there's more or less sort of even speed across time. And this is, I should say, log. So this is a really dramatic increase. This is a log increase in speed, decrease in speed with attention sequence length, whereas the locality sensitive hashing, pretty much even keel. You do not see this enormous logarithmic change in speed. It's a faster model by a lot. And the fewer hashes you have to do, the faster it is, which I think makes sense. Yeah, and then final conclusion. Reformer combines the modeling capacity of a transformer with an architecture that can be executed efficiently on long sequences, which is what this one is saying, with a small memory use even for models with a large number of layers, because they're not storing all of the attention weights for all of the layers, they're computing them every time. We believe that this will help large, richly parameterized transformer models to become more widespread and accessible. Also, the ability to handle long sequences opens the way for the use of the reformer on many generative tasks. So the longer the sequence, your input sequence, the better the generation's probably going to be, because there's more sort of data to kickstart it. In addition to generating very long coherent text, the reformer can bring the power of transformer models into other domains like time series forecasting, music, image, and video generation. So I think the big contributions of this paper are that they tackle both time complexity and memory complexity of transformers and get them way down, making them much smaller. And faster. is the other thing there. Yeah, good paper. I'm glad we swung back around to finish it. Yeah, I'd be interested to see some more. I mean, they had some experimental evidence there, but I'd be interested to see on sort of more varied types of NLP tasks and how well this does and sort of what the limits are. My gut instinct is because it can handle longer sequences, it will probably do better at a lot of types of tasks like, you know, anaphore resolution or something like that, where long distant dependencies are really important. And I mean, that's the thing that's exciting about transformers in the first place, right? Is that you can have these really long distance dependencies. Locality is not as big of a influencing factor on model predictions. So my voice is kind of starting to go. I don't know if you can tell. I'm going to call it here. Thank you for joining. I hope you found this helpful, exciting. Tomorrow we are going to be back with live coding, and I'm going to be working on sharing the assistant we've been working on for the last couple of weeks. That's a little FAQ assistant for me and my sort of like questions I get all the time. So have a great day. I will be back tomorrow at the same time, and I will see you then. Thanks for joining.